what is the wave function for a 2D infinite square well? So that's what I'm going to do today. And I've already made a video about the one-dimensional infinite square well, so you might want to look at that. Yeah, but here's a two-dimensional square well. So suppose I have x and y, and there is a two-dimensional box. So it has an x length of A and a y length of B, and then so everywhere past that little box inside of here is infinite potential, so you cannot exist outside of that. So with that, we can think of the following Schrodinger's equation. In one dimension, we had this. This says that the wave function, which is a function of x and t in one dimension, has to satisfy the following equation, which is really just the Hamiltonian with operators in there. So we have I h bar, the partial of psi with respect to t, and that's a capital psi, which means it has the time part in there too. This is the momentum operator twice, because it's p squared over 2m, it's kinetic energy. Negative h bar squared over 2m, the second partial of psi with respect to x, and then plus the potential, which inside the box is 0. If I want to move in 2 dimensions, I can't do this. I need the momentum operator in 2 dimensions. And so we get this following operator, del squared, and it's going to be equal to, in Cartesian coordinates, the second partial with respect to x plus the second partial with respect to y plus the second partial with respect to z. So with that, we can say the wave function psi is a function of x, y, and t. There's no z component. I have a two-dimensional well, no z component. So let's actually just first write this as some space part of x and y and a time part of f of t. I'm trying to think. Yeah, I'm trying to think if I should go ahead and split it into 3 things already. Yeah, let's just do that. So let's call this x of x, y of y, and f of t. So let's assume that we can separate out the function as though they are separable this way. If I put this all together, I get the following. I, h bar. Now I'm going to take the partial of this with respect to t. Well, these don't have a t in there. So I get x, y, partial of f with respect to t equals, now I have negative h bar squared over 2m. And I have the second partial with respect to, actually I'm going to get this whole thing operating on this. So this term operating on the second partial with respect to x, the only term in there is going to be this. So I'll write this as, let's write this as yf second partial of x with respect to x. That's a capital X, and that's lowercase x. Plus x, y, second partial of, xf. Second partial of y with respect to y. And then plus, there's no z, so I'm just going to get rid of that. And then I have plus v, and let's assume there's no time dependence here. This is going to be x, y, f. Okay, so now I'm going to do the same thing I did for the one-dimensional well, and I'm going to divide by both sides of the equation by x, y, f. So in that case, I get the following equation. So here I'm going to divide this by x, y, f, so I get I h bar 1 over f partial of f with respect to t. Here I get, that's equals negative h bar squared over 2m. Then I get, I'm dividing this by x, y, f, so I just get 1 over x. 1 over x, second partial of x with respect to x squared. Not x squared, second partial of x with respect to x. And then over here I have xf divided by xyf. I get plus 1 over y, second partial of y with respect to y. And then over here I just get plus v. Okay, so this is pretty nice in that right away we can see something here. This side only depends on space, assuming the potential does not change with time, and this side only depends on time. So the only way for both of these to be satisfied, I have a time part and a space part. They both have to be equal to a constant. So we're going to call this constant E. So let's take a look at that space part, the time part. So here I have, and this is exactly the same as what we did for the one-dimensional infinite square well. The I h bar 1 over f partial of f with respect to t is equal to E, which is some constant. So I'm going to multiply both sides by f, divide both sides by I. I get partial of f with respect to t equals minus I f over h bar E. So this says I'm going to take the derivative of f with respect to t and get the same thing back with this extra constant in there. So that means that if I say f is equal to e to the minus I e t over h bar, that will work. 'Cause now if I take the derivative, I get the minus I e t over h bar. So that's my time part of my solution. Okay, and that's exactly what we got before. Now let's go back to the space part. So here I have negative, I don't want to write it down wrong. Okay, so I have just the space part. Negative h bar squared over 2m. 1 over x, second partial of x with respect to x, plus 1 over y, second partial of y with respect to y. Equals E. Inside the well, V is 0, so I decide this is equal to E. Now, here's the thing. Again, I have two terms, right? I have a term that depends on x and a term that depends on y. There's no y in this term, and there's no x in that term. So the only way for these two to add up to a constant is that each one of those has to be equal to a constant. So I can say negative h bar squared over 2m 1 over x partial of x with respect to x, second partial, is equal to, we'll call that ex. And then so I'm going to say this is equal to ex plus ey. So that has to be true. So now if I multiply both sides by this stuff to get rid of this stuff, I get the second partial of x with respect to x is going to be equal to negative 2m over h bar squared times x. Ex. I should put the ex right there. Yeah. And let's let kx equals the square root of 2m ex over h bar squared. So now I have this, the second partial of x with respect to x. Remember, those are capital. Negative k squared, kx squared, x. Well, now I can solve that equation. And this is exactly what we did in the one-dimensional infinite square well. So this equation, again, the best differential equations, the best way to do it is to guess. And so if I guess a solution, then we could get that. Because what if I take the derivative of, what function do I take the derivative of it twice and I get a negative constant in front of it? And the answer is sines and cosines, both a sine and a cosine. So if I say x as a function of x is equal to a sine kxx plus b cosine kxx. And that's the solution, right? So if I take the derivative of this, I get sine, the derivative of the sine is cosine, but I get a kx in front of it. The derivative of this is negative sine, I get a kx. And then I go backwards to get another kx, so it does indeed work. Now we need to apply our boundary condition. So I know the following has to be true in the x direction. X of 0 has to be equal to 0, and x of a has to be equal to 0. So if that is because, in order for my function to be continuous, I know there is zero wave function over here because the potential is infinite, and zero wave function over here, the potential is infinite. So that means that at the boundary, it has to also be 0. So these two boundaries has to have a wave function of 0. And this is my spatial wave function in the x direction. So this is easy, right? If I put in x equals 0, then this says that b has to be equal to 0. So b equals 0. That's the only way, because this will already give me a 0. But the only way for this to be 0 is for b to be 0. But for this one, x equals a, I know that k x a equals n pi. That has to be true, right? Where n is equal to 1, 2, 3. So that puts a limit on the values of kx. So kx is equal to n pi over a. Okay, so now we have the following function. So I can write x of x equals a sine of n pi x over a. That has to be true. Now, there's something else that has to be true. If I look for this particle in the x direction, then I have to find it. So that means that the following has to be true. If I integrate from negative infinity to infinity, so this is the wave function, the probability density would be x star x dx. And if I integrate over that from negative infinity to infinity, I have to get 1. So I know that from negative infinity to 0, there's no wave function, and from a to infinity, there's no wave function. So this is actually equal to 0 to a of, and the complex conjugate of x is nothing. So I get a squared sine squared n pi x over a dx. And I don't want to do this integral. I've done it before. I've done it numerically. But the answer is that a is going to be equal to the square root of 2 over a. So now I have, this is going to be the square root of 2 over a sine, and that's actually, I need to call this nx because I'm going to get another n, and I'm going to have to distinguish them. So I'm going to call it nx, sine of nx pi x over a. So that's my x function. Now I need to do the exact same thing for the y direction. So let's write down my y differential equation. I have negative h bar squared over 2m, 1 over y, second partial of y with respect to y. It's going to be equal to ey. Okay, so you see here that we have the exact same situation. I mean, this is the exact same equation, except it has y instead of x. So I'm going to get the same thing. So I'm going to get y as a function of y is equal to, now the normalization, I'm going to go from 0 to b. That's the only difference. So I will have the square root of 2 over b sine of n y pi y over b. Okay, I'm going to do the whole thing because it's the same thing. Okay, so now let's put this all together. Psi as a function of x, y, and t is going to be equal to, remember, it's x times y times f. So my x is going to be square root of 2 over a sine nx pi x over a. And then I have times square root of 2 over b sine ny pi y over b. And then I get e to the negative I e t over h bar. Now remember, the e's are determined by e equals ex plus ey. And so we have, where did I put that? I keep forgetting what I wrote. So let's put it together. This is my wave function right there. That's what I want to look at. Now I could do the probability density, which would be psi star psi, and just like in the one-dimensional infinite square well, as long as they have just one energy value, then this thing will go. If there's only one value of E, then these I have a negative I E T over H bar and a I E A T over H bar, and they'll turn into 1. Okay, so I have kx equals nx pi over a, ky equals ny pi over b, and then I said, what did I say? Kx equals, so it's nx pi over a equals the square root of 2m ex over h bar squared. That was a substitution I made. So let's just square both sides and solve for ex. I get nx squared pi squared over a squared equals 2m ex over h bar squared. So ex is going to be equal to nx squared pi squared h bar squared, which this turns into h, over a squared 2m. Is that right? Just double checking here. I think that's right. Yeah. And then so h bar squared times pi squared is just h squared. Yeah. And then ey would be the same thing. In y squared pi squared h bar squared over a squared b 2m. So there's my energies, and then I have my wave functions. Okay. So I think what I'd like to do now is to plot this. Now, so if I want to plot the wave functions, it's a little bit difficult because it's in 2 dimensions, and so I actually have to do a 3-dimensional plot. So I'm going to make a contour plot, a colored contour plot in Python. Now, I like Trinket GlowScript VPython the best, but that doesn't really do 3D plots very well. So let's jump over here. I'm using Jupyter Notebook, and I'm going to plot this thing, and let's just see what happens. Okay, so switch over here to this. Okay, so here's my Jupyter Notebook. So the first thing I need to do is to import some stuff. I'm going to go import numpy as in p, import, and that's so I can do mathematical functions. Import matplotlib dot pyplot as plt, and that's so I can make a graph. Let's just run that, make sure it works. Okay, so now I need to pick my values. I'm going to use length in nanometers, and then I'm going to use all these, I'm going to use my energies in electron volts. Okay, so let's say A is equal to 1, and that's in nanometers. I'll put a comment there, nanometers. B equals 1. I can change that later. Now, so HC, I'm going to use units of electron volts. So I need to use, and I'm going to use mass in terms of electron volts too. So I'm going to say HC is equal to 1240. H bar C is equal to 197. And then I'm using an electron. So the mass of an electron in MC squared is 511000. Yeah. Oh, I need one other thing. Pi equals np dot pi. So pi is not built in to GlowScript, but it's in NumPy. So I can get, and I don't want to call it np dot pi because it's no fun. Okay, so now I'm going to say in x equals 1, in y equals 1. I need to calculate my energies. Ex equals nx times hc squared divided by 8. Did I have an 8? Where did my 8 go? Why do I have an 8 there? You know, I messed up my other term earlier. Yeah, there should be an 8 there. It should be 8 mc squared. So it's 8 times m times a squared. I'm pretty sure that's right. And then ey is equal to ny times hc squared divided by 8 times m times b squared. And then let's just say e equals ex plus ey, because I'm going to print that. Print e. I'm going to say I want to use my n and my x. Let's say nx ny equals in x in y. E equals E. It's in electron volts. Now let's just run that. Okay, so that's 1 energy level, and I get that's my 0.75. Now look up here, if I change this to 1, 2, I get 1.12. What if I do 2, 1? I get the same. And so this is where you get degenerate energy levels. So I can have two different states with the same energy, and that's kind of an important thing. But let's go back up here to n equals 1, 1, and we're going to plot that. Okay, so now I need to create a plot. So the first thing I can do is to make a range of x and y values to plot. So I'm going to say x equals np dot arrange 0 to a 0.01. So this will make values of x in an array from 0 to a by intervals of 0.01. And I mean, there's better ways to make ranges, but I always like this way, so I'm just going to keep it. And then the same thing for y equals np.arrange 0 to b 0.01. Now that's going to make one values a list of an array of 0 to a and an range of 0 to b. But if I want to make a 3D plot, I actually need a grid. And so this is called a mesh grid. And I could use the same variables again, but I'm going to call it new things. I'm going to say xp and yp is equal to np.meshGrid of x, y. So what this does is it takes my x, y values and then it fills in all the combinations. So I actually get a whole bunch of values. And I can use xp and yp to calculate my psi values. I know that's always kind of confusing. So let's calculate psi. Psi is going to be equal to 2 divided by, so if I combine those two normalization constants together, I get np dot square root of a times b, and then I have times np dot sine of nx times pi divided by a times np dot sine of ny times pi divided by b. I forgot the y. So I need to multiply this by x times xp. I'm calling that xp, and this is times yp. Why did I miss that? Yp. So that's going to generate a vertical value for all of those different combinations of x versus y on the plot. Okay, so now we're going to plot that. One of the things I would normally do, and then let's just show you. I'm always get scared. So if I go up here and make this a little bit smaller, so there's not as many points. I can print this and make sure it's working. And so see, there's all my x, y, z values, and it's just a 10 by 10, so it's not too bad. But let's change this to 0, 0, and not print it. Instead, we're going to plot it. So to plot this, we're going to make a contour plot. So that's going to be plt.contour f. So a contour f is, a contour plot has lines of constant psi values. A contour f fills in those lines in betweens with different colors. So I need to give it an x, I need to give it a y, and I need to give it a z, which is going to be psi in this case. I'll edit that a little bit. So let's give also a color bar, plot.plt.color bar. This puts shows you which colors mean which values. And so let's give it label equals psi. And then I need to give an x label, and that's going to be equal to x in nanometers, and a y label, and that's going to be y in nanometers. And then I'm going to show it. Then I'm going to plot it. plt.show. And let's see if it runs. Check that. That's actually really nice. I think I'm kind of pleased with that. So we can actually increase the number of levels for contour lines to make it look a little smoother, even though I think that looks actually pretty good. So if I go up to here to the contour plot and add levels equals 20, levels, then it looks even better. I could go 50 and it'd be pretty smooth. There you go. So you can kind of get a feel for what this looks like. It's a bump right in the middle, which is what you'd kind of expect. What if I go up here and change in x equals to 2, but in y equals 1? So now I have two humps in the x direction, but just one in the y. I could do the same. I could do 1, 2. Let's do 2, 2. And so now you get this. And so those dark areas are low and the yellow areas are high, because this is the wave function. This is not the probability density. If I wanted to plot the probability density, I can do that. I would just need to plot this squared. I think I can just do I have to square it right here? Let's do this. P equals psi squared. I think that will work. It might not work. And then let's just plot P. There. And so now they're all positive, right? They're all up. Okay. I'm pretty happy with the way that turned out. I mean, we can go as high as we want. We can go like, let's see, 5, 7, 4, 7. Okay, so that's your 2D infinite square well. 3D infinite square well would be the same thing. The only problem is it's difficult to plot, right? Because you can't really show that fourth dimension. And that's why I did 2D. Okay, so we can use this because we're going to talk about 3D for the infinite square well. For the hydrogen atom. But that's a little bit more difficult. So hopefully that's useful to you.